So that we understand exactly what we can learn from a rate law, I want to use a particular example, and that is the dissociation of N2O4 into two NO2 molecules, to illustrate this a little bit and talk about some of the things that we might look for if we were to graph some of the quantities we're talking about. All right, so what I've drawn here is a graph of the time evolution of this reaction as it goes forward. Okay, so on the vertical axis I'm showing the concentrations, and I should specify that this top one here is going to be N2O4 initially, and this bottom one is NO2 initially. Okay, so really all I'm doing is I'm creating a curve that shows me how the N2O4 starts from an initial value up here and then proceeds down this way toward eventually a final value over here. And similarly, NO2 starts at 0. I'm assuming that we start only with N2O4, that it then breaks apart and forms two NO2 molecules and ends up over here. All right, now let's talk about this diagram a little bit and see if we can understand, what sorts of things can we learn from this. All right, first of all, I think it's easy to see that reactants diminish over time. And that's generally going to be true for almost any chemical reaction, at least any one that I can think of. Okay, they diminish over time and products grow over time. And that's indeed what we're seeing in this graph. The reactant N2O4 is diminishing on this curve. It starts at a higher value and it ends up at a lower value. And it goes from one to the other fairly smoothly, and that's actually fairly typical. All right, the products, on the other hand, start at 0 and they move up and they get larger as a function of time and end up at a higher value. All right, so that's something that we can learn, just a very simple thing we can learn from looking at this graph. Now, what about the rate? What is the rate on this graph? How would we describe it? Well, let's suppose, let me get another color here. Let's suppose I'm interested in the rate at a particular time. Let's say this time here. So I'm going to draw a vertical line up from that time, and the rate is basically going to be related to the slope of these curves at the point where that line intersects the curves. So I might have one slope there and another slope here. Okay, now one thing to observe, the slope of reactants, reactant slope, is negative, and product slope is positive. Okay, and that's just another way of saying what we said in the first point there, that reactants diminish and products grow. They diminish because their rate of change, which is what this slope is measuring for us at this point and at this point, is a negative slope. So that tells us that the reactants are diminishing. Okay, the rate is basically an instantaneous slope. So it is a slope that is particular to a given instant in time. Okay, so that tells us that the rate actually changes as a function of time as the reaction takes place. All right, and since it is the instantaneous slope, once we calculate a rate, it'll only be that rate for an instant, and then it'll be a different rate because it will move on. Okay, and this is also in keeping with the fact that the rate is somehow proportional to the concentrations of the reactants and theoretically the products, but in fact we don't usually think of it as a function of the concentration of the products, but it is a function of the reaction of the of the concentration of the reactants. Now, another thing that I could tell about these slopes, and it's not easy to see the way I've drawn it here because I'm not a very good artist, but the rate or the slope of NO2, which is our product, is actually twice the slope of the N2O4. Okay, and that happens because every time one of these molecules falls apart, it produces two of these. So that means the rate of appearance of NO2 has to be twice as great as that. And that's what this slope means. So we should expect to see a steeper climb on this and a shallower decline for the negative slope. Now, I should probably also say that there's a negative sign here because these two, the products and the reactants, must have opposite signs of their slope. One is a negative slope and one is a positive slope. All right, now I'll also observe that at long times, what happens to that slope? Okay, that slope actually goes to 0 at long times. So in other words, we've got a level curve out here. I'm trying to draw it in red, it's hard to see in red, and a level curve out here. So the slope is about 0 in both cases. What does that mean? What does it mean when the slope is 0? Well, in effect, what's happening is that the rate is going to 0. When the rate goes to 0, in fact, this is a signal that we are at an equilibrium. So I guess another way to read this is that when we are at equilibrium, our overall rate, the net rate, must be equal to 0 when we are at equilibrium. So this is another useful thing to learn from this curve. Now, we have predicated the rate as basically being equal to this derivative of the concentration of one of the reactants. Now I've left out this necessary part, but it's a derivative. Okay, so in effect what we have drawn here, what we have represented, is that this is called a differential rate law. So it is dependent upon the derivatives, or the rate of change of the reactants. All right, what else do we have in terms of rate laws? Well, in fact, what we've drawn here, this diagram, is indicative of another kind of way of describing the rate law that we'll call an integrated rate law. And the integrated rate law is basically telling us about the time evolution of the reaction species. So differential rate law is all about instantaneous change, and integrated rate law is all about the long term. So if we were relating this, say, to a human foot race, the differential rate law would be, who actually achieves the fastest speed during the course of that race. Whereas the integrated rate law would be something about charting how far each runner was able to run within a certain amount of time. So it would be a global picture of the race more, not an instantaneous one. Okay, this is important to realize because these two rate laws are in fact related to one another. They have to be related to one another. And their names almost imply what that relationship is. They are related mathematically because the integrated rate law is essentially the integral of the differential rate law. Okay, so they provide, in some sense, they give us the same information about the kinetics of a reaction, but they package it in different ways. One is telling us how that rate changes as a function of time, but it's not really keeping track of where we are in the reaction particularly, whereas the other one is keeping track of where we are in the reaction, but it's harder to determine exactly how fast things are changing as a function of time.